Hey everyone, it's Alvaro Fuentes for the Stata YouTube channel, and in this video we're going to talk about the stationarity tests available in Stata. A weakly stationary process, which a lot of the time we just call a stationary or stable process, has a constant mean, not a mean that changes over time, a constant variance, not a variance that changes over time, and constant autocovariances, which means that the correlation between observations only depends on how far apart they are and not on the time period where we look. In time series analysis, many of the most popular estimation and forecast methods assume stationarity. This includes autoregressions, vector autoregressions, conditional heteroscedasticity models, and state space models, as well as estimation of impulse response functions. Other procedures, like those involving cointegration, assume non-stationarity. And certain models, like the unobserved components model, deal with both stationary and non-stationary processes. In all cases, it is important for us to be able to determine whether our time series are stationary. One way to check for stationarity is to check whether our time series is best described by a stable autoregressive model, where the coefficient is a positive or negative fraction, or by an unstable model where the autoregressive coefficient is equal to 1. A process like this, which we call a unit root, is a non-stationary series that wanders aimlessly without a constant mean or variance or autocovariances or really any discernible pattern. And because a unit root can take on any behavior, on a plot it can look similar to other processes, including stationary ones. So the question we will ask in a test for stationarity is whether our time series are in fact stable, or they just look like a stable process in the particular period we're studying. To test for a unit root in Stata, we can use the Augmented Dickey-Fuller test implemented in the dfuller command, the Phillips-Perron test implemented in the pperron command, and the Dicky-Fuller generalized least squares test implemented in the dfgls command. To understand the logic of these tests, let's talk for a minute about intercepts, drifts, and time trends. For the two stable series on the left, the effect of including an intercept in the equation is simply a shift of their constant mean away from 0. For the unstable series, on the other hand, adding an intercept to the equation causes the series to drift. The unit root is still wandering aimlessly, but this process now has a type of trending behavior, specifically the constant growth we see on the plot. A time trend causes the mean of all three series to change over time. Here we have added a linear time trend to the equation, and you can see that the effect for the unit root process is a new type of trending behavior, namely exponential growth, whereas the two stable series on the left now show linear growth. And it is of course possible for a series to have both an intercept and a time trend. Before we move on to our explanation of the tests, notice that the first two series are what we call trend stationary, meaning that the fluctuations around the upward trend we observe are actually a stationary process, whereas the series on the right is different stationary, which means that even if we were to remove the upward growth by setting alpha and delta to 0, and only look at the fluctuations happening around that growth, we would still have a non-stationary process. We'll come back to this distinction in a moment. Now we're ready to discuss the 4 cases where it is appropriate to test for a unit root with the tools available in Stata. In a typical setting for case 1, we have a series that looks like this, and we're wondering whether this is a sample that just happens to look stable around a mean of 0, but it's actually a unit root that will eventually diverge away from 0, or this is in fact a stable series fluctuating around 0. To test that, we fit a model with no intercept or time trend and test whether the coefficient on the first leg of our series is equal to 1. The prototypical situation for case 2 is very similar, except here we have a series that looks like it might be fluctuating around a mean other than 0. So the question we ask is whether this is again a sample that just happens to look stable, but it's actually a unit root that will eventually diverge away from this range of values, or this is in fact a stable series. To test that, we fit a model with an intercept, and again test whether the coefficient on the first leg of our series is equal to 1. Notice that the intercept in this case is only included to capture the possibly non-zero mean we suspect. But under the null of a unit root, we are still assuming that this intercept or drift term is equal to 0. An example of case 3, where both the null and the alternative seem plausible, could be a strange situation like this, where we're not sure whether we have a unit root with drift, or a stable process that just happens to look like it's drifting for the time period we have in our sample. Those two are very different series, and it's unlikely you'll run into a situation where theory tells you they are both plausible data generating processes. But this test can still be useful to check whether a series is a drifting unit root or it is just something else. The model we fit in this case is the same as in case 2, but here we are not assuming that the drift term is equal to 0 under the null. And again, the unit root test is simply a test on the coefficient of the first lag. Finally, in case 4, we suspect that the series is trending, either because it looks like it or because theory tells us it is, but we aren't sure whether the process is a drifting unit root or even just a unit root without drift that happens to look trending in this time period, or whether this is actually a stable process that is fluctuating around a time trend. To test that, we fit a model with both an intercept and a linear time trend, and again test whether the coefficient on the first lag of our series is equal to 1. Notice that in this case, the series under the null is difference stationary, and under the alternative, it is trend stationary, which is an important distinction in many applications. Once we have determined what question we want to ask and which null and alternative hypotheses are appropriate to ask that question, the options of the dfuller, pperron, and dfgls commands give us access to these 4 cases. One last comment before we move on to our example in Stata. If you look at the math of these tests in the Stata documentation or in other resources, you'll notice that the explanation we just presented was slightly simplified. Specifically, you'll notice that the tests actually run a regression on the differences rather than the levels of our time series. And because of that, you'll also notice that the discussion is usually about the parameter of the first lag being equal to 0 rather than equal to 1, but it's not difficult to see that this is equivalent to the hypotheses we presented in this video. Okay, so let's look at an example in Stata. Here we have downloaded the annual series of the Gross Domestic Product, or GDP, of Ukraine, which is available from 1987 to 2024 on the repository of the Federal Reserve of St. Louis. And the series looks like this. The upward trend we see on the plot is expected, because a country is usually able to produce more and more as technology advances and the population grows. But a key question in applied macroeconomics is whether GDP is a drifting unit root, which is simply drifting upwards as it wanders aimlessly, or a stable process that we can actually model and forecast around a time trend. And you probably already noticed that this setup is a perfect fit for case 4 of the unit root tests. So let's go ahead and try to answer this question. To test under case 4 with the Augmented Dickey-Fuller test, we type dfuller, then the name of our series, and specify the trend option. Stata tells us we're running the test with only 37 of the 38 observations in our sample because we're fitting a model that involves the first lag of the series. No lags of the first difference of our series are included as controls in the model by default, but we can change that with the lags option of the command. Remember, the null hypothesis for case 4 is a unit root with or without drift. On the table, we can see our test statistic and the critical values for 3 popular confidence levels. And because the statistic is not beyond, or in other words, more negative than any of the critical values, we do not reject the null hypothesis in this example. The approximate p-value at the bottom agrees with this decision, but keep in mind that Dicky-Fuller critical values and the McKinnon approximate p-value here are computed with different methods, so they may not always agree with each other. The Phillips-Perron test is an improvement upon the Augmented Dickey-Fuller test that offers robustness against serial correlation and heteroscedasticity in the model we fit. It does this by using Newey-West standard errors in the calculations. The table reports 2 test statistics. Including none of the so-called Newey-West lags, the CT statistic at the bottom and its critical values would be identical to the Augmented Dickey-Fuller results we saw before. And the Z-row statistic above is another popular version of the Phillips-Perron test. Both statistics here and the approximate p-value again suggest we have a unit-root process. Finally, the Dicky-Fuller GLS procedure is another improvement on the Augmented Dickey-Fuller test meant to increase power. This method first detrends our series using a generalized least squares model, and then applies the Augmented Dickey-Fuller test to the detrended series. We can see on the table that models were fit using up to 9 lags of the first difference of our series as controls. That number of models was determined through a rule of thumb called the Schvert criterion. We can then read here the test statistic from each of the models and the corresponding critical values, and in this example, all 9 test statistics agree on the same answer, but for situations where they disagree, the bottom of the table reports 3 lag order selection criteria. The Schwartz and the modified Akaike information criteria, which in this case suggest 1 lag is the best fit for our data, and the sequential T algorithm of Ng and pperron, which in this example actually suggests we remove all lags, specifying the max lag option. So, for our annual series of the GDP of Ukraine, the Augmented Dickey-Fuller test, the Phillips-Perron test, and the Dicky-Fuller GLS test all agree this is a unit-root process. For more information about these testing procedures and more examples, remember you can always type help and then any of the commands into the command window and click on View Complete PDF Manual Entry. We hope this was helpful, and thanks for stopping by.